Yeah, it started. So please, Rajdeep, over to you.
Yeah, thanks a lot, Ritesh and Partha and the organizers for
Yeah.
inviting me
Is it
to
possible to increase the gain of your voice?
uh, gain of my voice. Yes, I'll try to increase the gain of my mic.
Okay.
Hi, any better?
It's quite low. I'm on the max on my computer. Maybe I'll try using the headphone. I might be able to hear better. Anyway, you continue.
Uh, I'll try to talk louder if that helps. Um okay, so let's get started. Um, So today and this afternoon, we'll be covering what traditionally we call machine learning, but not deep learning. But the purpose of these two lectures is to have the groundwork ready. That what are the metrics, what are the considerations that we should all be aware of when we are trying to design some algorithm to solve the kind of problems that we are dealing with. But also to be aware what are the pitfalls that must keep your eyes open, so that we don't just apply these models, these very powerful models and tools as a black box, but also have our eyes open to how they are doing what they are doing. So I'm going to start with what I call basics of machine learning, and then I'm going to tell you what are the topics that we will cover in the two lectures. I believe all of you have gotten an email that I have sent to you, which is in terms of sort of you can say a benchmark data set that we can use to study all the different kinds of algorithms that we consider. So to decide whether one algorithm is better than the other, you should keep something fixed, right? So in this case, we are going to keep the data set fixed, and then you can apply each of the different algorithms that we learn, or the same algorithm that we are using with different kinds of optimization, to see how the performance metrics change for this data set. At the end of the class, I'm going to just walk you down that particular data set that we will do in the tutorial session in the afternoon. And I've also sent a couple of Jupyter notebooks, so please keep those downloaded. Okay, with that, let's get started. So, what I want to first talk to you about is what I call elements of supervised learning, because that's what I'm going to cover for you. There can be unsupervised learning, there can be semi supervised learning, but for the basics, we are going to keep it simple. We want to cover elements of supervised learning. So, for that, I have to define for you the, let's say, the mathematical problem. Then sort of I have to sketch a flow chart or a general algorithm, and then define some kind of performance metrics that generally classify whether a model is doing well or not well, what are the problems, etc. So this is what we will start with right now. And then we will cover two algorithms in the two lectures. One is what is called as support vector machines, and the second what are called boosted decision trees. The idea is to sort of cross compare like both of them are achieving the same general task, but with very different assumptions and techniques. But you will have a same data set to apply them and take a look at how they perform. So that's more or less, as am telling you, that's more or less what our goals are in these two lectures. Okay, so let's get started with the first topic, which is the elements of supervised learning. So essentially, we have a data set that is classified. So in supervised learning, we have labeled data. So what does that mean? That data is characterized by a certain vector, which I'm calling xi. That is say, a vector of input features. And then I have a certain, so I have also, so xi rather. Okay, so I have many data points, and for each data point, I have different input features. And then I have a target that can be discrete or continuous. Or continuous. Okay. So attached to every data point, so you have a data set. So think of, say, columns and rows, where each row defines one of, say, n data points. And then you have, let's say, a certain number of xi's, x1 to xm, let's say. There are m input features that define a point. Let's say if we want to study people, whether or not, say, they play video game or not. So you can have gender, you can have age, you can have which region of the world they live in. These are all potentially input features. The input features themselves can be discrete, can be continuous. There's no problem on that. But for every point, I must have a label. Do I play video game or not? So that's a discrete label, but also it can be continuous. Let's say I want to predict the price of a stock, right? Based on some other parameters. So that price, which is your target, that's a continuous number. So your target can be discrete or continuous. And then the goal of the problem, the goal of the machine learning, what the machine has to learn is, on the training data, you put in these x's. So there are n such points, you put all of them in. So let's do I1 to xin. So you put all these data points into this machine. I'm calling something called theta that I'll describe later. And the final goal is, when it has been trained, so there's a concept of training, it will spit out an answer for each of the points. Okay, that's broadly what the goal of the problem is. So then what you do is, you have to split your data into what's called a training sample, where effectively, let's take a simplest case. If I have a linear model, then these, okay, I'm changing the definition. I'm calling this yi hat. Okay, so suppose I have a linear model, then, oops, what happened here? I don't know. Okay, so suppose I'm doing a linear fit on three-dimensional data, right? So there, what is the model trying to learn? It's trying to learn a slope and an intercept, right? You know what are the x1 in three dimensions, x1, x2, x3 of the points are, and you know what the corresponding sort of the y value is. So based on that, you are trying to sort of learn these theta ij's. So then, even if you have an unknown data that you haven't seen before, you carry out an operation like this to get a prediction. Okay, so this is the simplest example just to set your mind going. But in the most general case, you are not limited to linear models. It can be any model, but the whole idea is you have to carry out a certain operation so that when you input an previously unknown set of input data, particularly in terms of its input features, you feed them into the model spits out an answer. It can be a discrete answer, then those become what are called classification problems. It can be a continuous answer, then that becomes what's called a regression problem. So that's sort of what, in a very hand-waving way, sets the stage for your supervised learning problem. That you have labeled data, you want to learn, I wouldn't call it a function, but you would want to learn something that you put in input features that you have chosen. You undergo what's called a training, where there's a certain label known to you, and the model knows then how to predict suitable answers for given input features. Now, once you have trained the model, you know the mathematical operation that if you have an unknown data, you put in the input features, it gives you an answer. Okay. At this stage, are there any questions? Because this part is important. Once it's out of the way, then we can make things more fun. So, if there are any questions at this stage, please let me know. No. Okay. So let's.
In the first box, you have written theta ij, and the second box, you have written the model as n. Both are
Sure.
same or different?
Yes. So theta ij is like the way I've written it. This is only encoding a linear relationship between the target and the input features, right? But as I said, this need not be a linear relationship. I may not even be able to write out a closed form expression. So that's why, in order to generalize it, I wrote it as M. So theta ij is a special case of M, but M can be a general nonlinear model, which you may not even be able to explicitly write down as a closed form equation.
Okay.
Sir, here
Hi.
here the vector xi consists of n data points like xi1 to xin. Are there n data points in each vector?
No, that's M. So the number of input features that you have, right? Just think of a straight line fit, right? Let's say two-dimensional straight line fit. I can have 20 points, but each of them have independent x values. For each of those x values, there exists a y value, right? If you take it in 3 dimensions, then I have, let's say, a x value and a y value. I want to have the sort of the z value, sort of. Okay, so that's why I wrote two expressions. One denotes the index over input features. Some people are writing on chat. It's hard for me to follow, so you have to ask a question. So I can be any number, so M, but the number of points or your training set that you have, that's an independent index. So that's why I call it as N. So they have no relationship with each other.
Okay.
I mean, of
Thank
course, you expect N to be much larger than M. I mean, otherwise it's hard to learn, but they are independent. Shall we proceed? Yeah.
Sir, what was the data set being labeled mean?
So the data set being labeled means, again, in the straight line context, 2D fit, for every given X coordinate, there's a Y coordinate, right? So the model that you learn has to predict this. But in principle, you can have unlabeled data. Let's say, let's take a concrete example. So I have a detector, right? The detector has, say, 4 crystals, so 4 channels of output. Sometimes the detector, say, is not functioning well, noisy, right? But in that case, I need not know a priori whether the detector, event by event, the data set that we have, if the detector is noisy or not. So I just have the outputs of 5 crystals at different points in time. And the goal of my algorithm will be just based on these 5 numbers to tell me in a given event that whether you have some real energy deposit or is this all noise and it's not functioning. So there you just have Xi's, and just based on the Xi's, you have to predict, am I noisy or not? In the case of label data, suppose I have further information based on my knowledge of the detector. If there are these combinations of inputs, is it noisy or not? Then for those inputs in a per event, I will have an additional flag, noisy or not noisy. So the training problem, the algorithms become very different whether your data is labeled or not. Clustering is one more example. If I just have points clustered in space, if I do unsupervised clustering, just from these points that are clustered, I have to say whether they belong to one class or the other class. In the case of labeled data, this information is already provided to me that for at least a subset of the data, for instance, that based on certain values of these input features, they belong to some class or the other. Okay.
Okay, sir.
Okay, so let's make some progress. So the main point is, now we come to these labels. So you need judicious choice of these YIs, depending on if it's a classification problem, in which case these are discrete, right? For those of you who work in high energy physics, say I want to look for a Higgs process. So am I Higgs signal or am I background? So the label is discrete. On the other hand, in a regression problem, the label is generally continuous. Let's say for electron or photon incident in a calorimeter, what is the energy of the original electron? So the energy of the original electron is a continuous number, right? So I can simulate events with different values of true energy of the electron, and these become incident in the calorimeter. I can define input features in the calorimeter, energy deposited, etc., etc. But per event, I know what the true energy was. So based on this, I can train the model and I can apply it. But the main point is, here it is continuous. You can also have a case where you're just trying to rank based on that, you have different problems. So your task in your training becomes to find the best values of M that given x's you predict yi. Okay, so algorithmically, in order to do that, you then have to define what's called your training objective. Okay, and in general, the objective, we'll see this explicitly, but I'm trying to set the stage, will consist of two terms. This is called the loss term, and that is called the regularization term. Okay, so you must have come across different kinds of loss functions. For example, you must have come across, let's say, the mean square error loss. So say L, I'm saying M being the model, is say yi minus yi this whole square. Okay, what does this? And this is sum over data set, say 1 to n. So once I have a model, given input features, it predicts some value, right? For that same event, the data has a label yi. So effectively, your goal becomes to minimize this so-called objective, right? So you can see that this is a valid choice of a loss function. What you're trying to do is you're trying to tune the parameters of the model so that this LM becomes the smallest, or the deviation between the known labels and the ones you predict become the smallest. You would also have come across, if you haven't, we'll of course discuss this, what's called the logistic loss, which is more popular in classification problems, which is defined again, sum over the data points. This is defined as yi log 1 plus e to the power minus yi predicted plus 1 minus yi log 1 plus e to the power plus yi predicted. Again, not going into the physical interpretation, all that we will see going forward. Those of you who have come across something like what's called a binary cross entropy, you would have seen this kind of a form. But most importantly, we will see that extremizing or minimizing a form of this is just like doing a maximum likelihood fit. So these are very simple physical interpretations. So there comes the, then like one could argue, then I should be done, right? I minimize this, I get a model that best predicts whatever data I have, I should be done. But no, you're not done, because you need something to control the complexity of the model. Okay, so that's where your omega comes in. So let's say I have some data that I want to fit. In principle, if I only, sorry, how do I get rid of this? Eraser. If I only have to minimize the loss function, I can use an infinite order polynomial, right? So that would lead to what we call overfitting, or a completely biased model, which may not have anything to do with the underlying physics or the underlying dynamics of the model. So we absolutely, therefore, need to have some penalty that penalizes you wanting to have a more complex model. If something that's less complex can solve your problem, I should not go to something more complex, and always fall back to this fitting example. So suppose, what happened? Suppose I have some points that I want to fit Y. A certain model might fit it, but if I keep increasing the number of free parameters in the function I'm using, what I said, infinite dimension polynomial, that will also fit, that will give you a better loss function. And you must have come across this exercise, that the metric we use for goodness of fit is what we call reduced chi-square, where the denominator is not just number of points that you have, but you subtract it with the number of free parameters in the model that you have, to penalize you going more complex when you don't need to. So that's really what the purpose of having a regularization term is, to penalize more complex models. And the general topic here is called what's called the bias variance trade-off, where the idea is that you want the simplest model that is also predictive. Okay, so we went one step further. That is, now I have label data, I have a certain data set. I want to learn the parameters of the model. How do I do that? Clearly, I have to do some kind of a fit where I have an objective to minimize, which contains of two terms, a loss term that wants my predictions to be as close to the known labels as possible. I've given you two examples of losses. The first one is more common for a general regression problem, the second one for a classification problem. But I also have to be mindful of penalizing wanting to go more complex, so that I don't get a biased or an overfitted result. Any questions for this part? Because then we'll jump to the final part before going to algorithms. I wait 5 seconds more. If I have no questions, then I go to the next part.
So
Okay.
how are we determining this MSE and the logistic loss?
Louder.
So how are we determining this MSE and this logistic loss? I mean, the formula.
So the logistic loss we'll see has a very nice. So in general, like the logistic loss is sort of, you can back calculate that ultimately if you are doing a fit, right? What gives you a good fit? You know that if you have, you must have done in your statistics exercise, that a maximum likelihood estimator necessarily gives you an unbiased good fit. The logistic loss, we will hopefully see in the afternoon session, effectively boils down to a maximum likelihood fit of the data points when you have two classes under some approximations. So that has a nice physical meaning. In the case of a regression, if you see yi minus y predicted square, that kind of has the dimensions of a standard deviation. So in a regression problem, what do I want to do? I want to minimize the error between a label and my prediction, right? So that's kind of what motivates this kind of a form. Sometimes we are interested in relative resolution. So you might want to sort of divide this by yi predicted as well. So this is sometimes called mean relative error. So in the most general case, It depends on the problems that you're doing. If in your problem there is something that supports this minimization, you would choose that. Here I've just written out the two popular ones to use. I will highlight in the afternoon session the pitfalls of them. But the second one has a very nice physical way of looking at it. It simply comes from a maximum likelihood estimator. Okay, yeah, thanks. Anything else? Doesn't seem to be. Okay, let's make some more progress. So I'll very quickly tell you that whenever you train an ML model, it doesn't matter what that model is, there are certain things that you must immediately check. There's one thing called a receiver operator. It's called. So in the last ML school, I didn't know why it was called this receiver operator characteristic, but then I found out it's got to do like with signal processing. That's where it was first done. So now I'm assuming you have trained some model, right? What does this model do? You feed in any data, xi. This is one data point. You feed it into this black box of the model. It predicts for you y for that data. Okay, let's call it xij. For the jth data point, you have xi input features. This will predict some value. And if it's predicting, it's yj. But you also know what the true value was. So what you have to make is a plot of what, there are many ways of looking at it, but you will see true positive versus false positive. Before I come there, so effectively, when you have trained a model, let's say in a 2-class classifier, okay, you have trained some model. The model can predict a score. How probable am I to be class 1? How probable am I to be class 2? For a good model, you should get a good separation between the two classes. Okay, let's call it signal. Let's call that background. This M is the model score. Okay, now what effectively you do is then you determine where in the model you want to operate. Suppose you want the purest possible category, that I really want the purest set of S. So I will, and in general, you can always take the domain to say from -1 to 1 or 0 to 1. Okay. So again, repeating, once I have trained the model not just tells me am I class 1 or class 2, you can make it to say how probable it thinks it's one or the two classes, and it need not be 2, it can be more than 2. But for simplicity, let's consider 2. So then effectively I can draw these probabilities, and then I have the ability to define these boundaries, right? I want to operate in my problem for values above this. So what does that mean? That so if you operate here, you would be losing some of your signal, right? You'll be only taking up you'll be losing some of your signal because you are operating to the right of, let me put it in a different color. How do I do that? Right. Say you're operating to the right of this boundary. Okay? Yeah. So then you'll be losing some signal, but you will be also picking up some background, right? So I wrote it in rate or false positive rate. So this part that you see here, I can't point. This part that you see here, This is false positive, right? And this part is your true positive. So when your true positive rate is high, you want your false positive rate to be low. So typically you get curves like that. And many people plot it as 1 minus true positive, 1 minus false positive, then the whether the curve is convex or like whether it goes down or whether it goes up changes. But the main message is, for a good model, when my true positive rate is high, did I do it incorrectly? When my true positive rate is high, no, I'm doing correctly. When my, when my true positive rate is high, my false positive rate has to be low. Okay? And if you do it and then you have something called the area under the curve. Okay, in this case you have to take it like that, unless you do it as 1 minus. So highest is your area under the curve, better the model. Now suppose your model is not predictive at all, it is pure chance, then it's effectively a straight line, right, at 45-degree angle. So this is pure luck. And you cannot do worse than this. Like suppose you're above that straight line, you can always invert your prediction. The worst prediction is pure chance. Like randomly, half the time I predict correct, half the time I predict wrong. It cannot be 40% I predict correct, 60% I predict wrong, because then I'll just invert it and get a better prediction. Okay? So you are bound to do this ROC curve separately for the train and test sample. Okay? And your AUC, so basically if your test sample, I divide my sample into two parts. One, I do the fitting to get the model on. But once I have the model, I can do this prediction on the test sample as well. Your test sample should overlap the ROC. So this is the ROC, this is the ROC curve. Many ways of doing it, but broadly I told you what it is. True positive rate versus false positive rate. And I didn't say it. So each point on the ROC curve, so each point on this ROC curve here corresponds to a given value of this plot over here. So basically, when you have the two probability distribution functions, as you slide across, you effectively generate the curve that you have, the ROC curve, right? Because your true positive rate and your false positive rate is a function of where you're cutting the model. So you have to do this for both your train and your test sample. As long as they overlap or reasonably overlap, you're happy. That means there's no sign of overfitting. If they deviate, so for instance, if this is train, and let's do it in a different color, let's see. If this is test, suppose, your test sample. So what did I draw here? That for a given true positive rate, for a given true positive rate, my train has a lower false positive rate than my test. That is clearly overfitting, right? Because it would mean that effectively for the test sample, I have more background coming in. I should have comparable or better false positive for a given true positive rate. For a given true positive rate, if I have more false positives, that means the test sample has clearly something that is not there in the train, which is potentially a sign of overfitting. Okay, so doing the ROC curve both for train and test is the best check you can do for overfitting, and always track the area under the curve. Area under the curve in itself doesn't give the full picture. Why? Suppose I have, again, TPR, FPR. I have one like that. Now, suppose for whatever reason, I have something like that, right? It is better in some region, it's worse in another region. So the the AUC might be the same, but that doesn't mean that there is no overfitting. Okay. I hope this is clear, or if there are any questions, I can address it, because so this is really what I wanted to cover about the metric, that at the very least, whenever you train a model, this is the first thing that you should do for your train and your test sample. It tells you both the quality of the training, how predictive the model is, and whether there's any overfitting or not. If there are any questions, I can address it, because after this, we will move to our first model. I've seen questions in chat. There's absolutely no way for me to track that. I have too many devices open. Okay, doesn't seem to be any more questions. So I'll move on. Just for your information, I'm just noting, other than the ROC curve, and I'll cover that in the afternoon once I have a particular example, there's something called a precision recall curve. Slightly different information, so PRC. So just keep that in mind, that ROC in itself doesn't have the full information both about the performance of a model, whether or not there's overtraining. There's one more curve, but I just want to do it after I cover the BDT and the SVM. Okay, so there were no questions. So shall we move to our first model? With this, is someone talking?
Yeah, sir. Can I ask a doubt?
Yeah.
Yeah, sir. So regarding the ROC curve.
Yes.
So for actually, how you are actually choosing a particular point for the operating for the operation?
Repeat. How are you choosing
a particular point for operation?
I'm sorry, guys. Listen. Please don't send questions on chat. It's like there are pop-ups, but there's no way for me to follow. If you have a question, please ask. Yeah. Sorry. Go on.
Sir, can you go to the plot actually?
Go to the?
Yeah. Okay. So in the plot, in the ROC curve, actually, you are choosing a particular point for the operation, right?
That's in step 2. So let's go through the argument once more, and then let us know if there are questions. Let me write it afresh. So I have trained. So okay. So let's do it properly. Let's do it because this part is important. Let's do it carefully. Okay. So I have a data set. Okay. What is the data set? It's a collection of xi's, yi's, n points. Okay. This is the input feature. Y is the target. I split this data as I have to, so that I have an unbiased test. You split however you want. Some people use 80-20, 90-10, 70-30. So you split in train and test. Okay. You fit your model using that objective method by minimizing that objective on the train, and you get M. M is an abstract quantity which has a certain number of free parameters. But when you hit M with X, M doesn't care whether you're giving it points of the training data set or the test data set. Once it has been trained, you give it an X, it gives you a Y. Of course, you have trained it, it has minimized the training loss plus the regularization term. Okay. So now that you have trained M in a classification problem, not only does the model tell you, the model can't really tell you, am I one class or the other, right? It's naturally, it tells you how sure it is one class or the other. So it tells you what is the probability you're class 1 or class 2. So in general, in all algorithms, you will be able to output a score, which to sort of link it to probability, you map it in, say, 0 to 1 or -1 to 1. So suppose for class 1, I'm calling it signal, it gives a score like that. And for another class, background, it gives a score like that. So the model doesn't care how you want to use it. So now you have to apply your judgment for the problem that you're dealing with. Suppose your goal in your problem is that I want the purest one category as possible. So then I will operate as much to the right over here as possible, right? When I do that, the cost I pay is I am losing so much of my signal. But the gain that I have is the background that is faking is really tiny. But I can have an alternate thing. No, I do not want to lose any signal. I want to take all my signal. So then I might want to operate at that point. So then I have a high signal efficiency, but I'm paying a price that a lot more background is creeping in. I'm saying your operating means once I have the model, whether I call something a signal or not means the value of the model is above this number or above that number. Based on the value I choose, I get a certain signal efficiency and I get a certain background efficiency, which is nothing but true positive rate and false positive rate. So which point I operate in, there are additional criteria that come in, which is specific to the problem beyond what the machine learning training is. Then how do I get the ROC curve? Effectively, you scan the values of the model from 0 to 1 with some granularity. For each of the points that you scan, you get a true positive rate and a false positive rate, and you plot them. Right? It's these two curves together that make sense, because in the ROC curve, what you're doing is you're parameterizing out the value of the model or the score, the output score. So for each value of score, if you choose greater than that, you get 1 point on the ROC curve. Okay? But where you operate, that is based on the problem you're solving. Whether you can afford to have some false positives creeping in, or you really want to accept every single signal that you want. Is that clearer?
Yes, sir. But I'm asking that. So for particular values of theta, for the particular values of parameters, you will have one ROC curve, right?
No. Once the model is trained, you can't change theta. So once you have trained a model, the model parameters are fixed. Okay? So then this curve that you're getting, what's changing is the input data. So then you're feeding every single data point and you're producing this distribution. So the model parameters are all fixed. It's for different xi's, it is giving a different score. how much it thinks is, how probable it thinks it's S, how probable it thinks it's B. And then by cutting at different values, you reconstruct that curve. Model is fixed.
Okay, got
And
it.
that curve is called ROC curve. There you have shown a train curve and the test curve.
That's the additional check that you do. So if I have different, if I break my data set into 5 parts, I can produce 5 of this plots and I can produce 5 ROC plots. Okay, but the train test check is to ensure there is no overfitting. Like I said, if there's no overfitting, the test ROC will, as close as we follow, it will overlap the train ROC. And I gave that example. If the say the test ROC is below, what does that mean? For a given, for the same value of true positive, if this is the test, your false positive is higher, which means it is, the model is performing poorly, which likely means you have overfitted.
So, when we are talking about test and train samples, is it necessary that the data set, I mean, a particular data set is split into test and train, or two different data sets can be used as test and train?
I mean, what's the difference? You take
So,
one data set, you split
say
it
the
randomly.
property is different. Say the luminosity of one data set is different.
Let's not get into specifics of the field. Just
Oh,
try to speak in abstract terms. If the underlying, the main thing is based on everything is based on some underlying process.
yes.
If the underlying process that gives rise to that data set, what you call like the population in some sense,
Okay.
if they are the same, you can have it done 2 different ways, it's fine. But in that scenario, whether you but you have to randomly split, by the way, you have to shuffle and then split. It cannot be that you take the first 10% and the next 90%. It has to be done after shuffling.
Yes. Okay. Yes. Thank you, sir.
Okay, so I think I took much more time than I wanted to for this part, but it's important to do it once. So shall we move to our first algorithm? Okay, well. So the first algorithm that we're going to talk about is what's called support vector machines. I'll probably send you some slides later on some interesting history of this. But broadly, this was invented by Vladimir Vapnik in the 1960s. So he was like in, I think, Moscow State University doing a PhD where he had done all the mathematics of this, but it went completely into oblivion until in the 1990s, early 1990s, he moved to Bell Labs in the US, did exactly the same exercise. And then at that time, like this MNIST data set, those things were, so this digit recognition was being worked on. And this particular model, Vapnik's support vector machine, performed exceedingly well in this kind of a task. And that's when it gained popularity, but it somehow has also fallen out of popularity. Let's say, all through the 2010s to the 2020s, that decade, in all these collider problems, people use BDTs, DNNs, etc. No one even, I don't even know anyone if they use support vector machines. But recently it has again gained popularity because when you make quantum versions of these machine learning algorithms, so what's called the QSVM, which unfortunately we can't cover, it's much easier to have a quantum version of a support vector machine than many other algorithms. So of late, this has again gained popularity. Okay, with that introduction, let me tell you what the problem in the case of a support vector machine we are trying to solve. Okay, so I have 4 data points, and they can be one of 2 classes represented by pluses and minuses. Okay, you can see, and these 3 things that I have drawn are the same thing, and it has 2 input features represented by the 2 axes. So what is the purpose of the model? The purpose of the model is, now after this, if I get any unknown data will fall somewhere on this 2-dimensional plane. So if I get any unknown data, the purpose of the model is to tell me, am I plus or am I minus? Okay, so what support vector machine tries to do is, it's a class of model where you will see that there is no traditional loss function as such, but it wants to calculate what's called a decision boundary. Okay, in which space? The space of input features. If I have n-dimensional input features, it will be an n-dimensional decision boundary. So, like, suppose what you will later see is okay, let me just draw. Okay, I've drawn 3 different options. Not algorithmically, I've simply drawn. In one case, I've drawn lines which are perpendicular to either of the axes. In the other case, I've drawn a line that has a slope. And in the third case, I've drawn 3 lines. But broadly, what could be the purpose of the decision boundary is, if any point is to the right or up or down that we have to define, once I come up with such a boundary, if any new point is to the right of this, any new point, I will label it plus. Likewise, to the left, I'll label it minus. Similarly here, if any new point comes here, I will call it plus. If it comes there, I will call it minus. So the purpose of the training becomes, how, given the training data set, how do I come up with this decision boundary? Once I come up with the decision boundary, then all I have to say is, are you to the right or above or below me? Any new point, I will label it as such. So that became effectively the class of the optimization that a support vector machine falls under. Given input features, label data, please find a decision boundary so that I can then classify what I fall under. So the topics we want to cover are decision boundaries, widest street approach, and finally what are called kernel functions. Okay, so let's do the thing again. You can call this x1 and x2 if you want. These are the 2 input features. Suppose I have points like so, and I have points like so. Effectively, what I want to do is okay. Let me just set the formalism first, and then I will. And then this one. Okay, so let's go through the formalism that I've drawn. So on a two-dimensional space, I've jotted down a few points, okay, with pluses and minuses. Any arbitrary point need not be what exists. Any arbitrary point is denoted by this x vector. I have, while not formalized, effectively drawn a road that passes through one each of the points of either class, and then I have defined a midpoint of that road denoted by this vector w. Okay, so now you can clearly see that my decision rule. So like we discussed that once I get a boundary, then if I am to the right of something, I am one class. If I'm to the left of something, I am another class. Mathematically, how do I do it? I simply take a dot product of the arbitrary vector with respect to the w and demand that it is greater than equal to c, right? Why greater than equal to c? Well, x dot w equal to 0 means I am on the road, on the midpoint of the road. So to call it plus or minus, I want some offset with respect to that. So I always want to have a no man's land region, and that's what this C controls. Okay, so I can write this more generally that if, by the way, is the formalism clear? Two classes, I have drawn 6 points. I am trying to have a model that will implement a boundary that will maximally separate the two classes. And then if I have an arbitrary point, once I know the boundary, which is determined in this case by W and C, W determines the middle point of the road, and in some sense, C determines the thickness, the width of the road. Once I have this, I have a decision rule. If you satisfy x dot w greater than C, you are one category. If you are below that, you are another category. So that's the formalism that we are developing. So one can make this more formal, that if I'm changing terminology a little bit, if x be greater than equal to 0, then you are plus. If x dot be less than 0, then you are minus. The reason I'm doing it this way is effectively your decision rule becomes just the sine function of x dot w plus b. Okay, so the entire problem then becomes, how do I obtain w and b? Because once I obtain w and b, any arbitrary point, I'm just going to plug into, okay, let's call this the decision rule. So for any arbitrary function, I'm simply going to plug into this formula here. If it gives me plus, I will say your like signal type. If you're minus, your background type, or plus or minus. Okay. And then this is pure definition. There's nothing more to it. We define what are support vectors. So we define a positive, it can be it's not positive or negative. It is one class or the other class. Because I wrote them as plus and minus, I'm causing them positive support vector or negative support vector, where I'm using this terminology. Okay, it's purely definition. My decision rule is sine of x dot w plus b, but I'm defining the positive support vector as an arbitrary point. It may not exist. This point may not exist in your training set. Generally it will, but it need not. X dot w plus b as plus 1 and the negative support vector as minus 1. Repeating plus minus denotes the two categories. Okay. To bring in some more terminology, so I can define also yi such that yi equal to plus 1 for positive classes and minus 1 for negative classes. Okay. So why did I do this? Because I want a closed form equation. So I don't know, call this equation 1. So now with this terminology, what I'm implementing is, so suppose you multiply both equations on both sides by yi. Okay. Understood? Yi that you have defined as plus for positive class, minus for negative class. Now you multiply both sides with yi. So you will get what happened? Yi x plus wi plus b equal to plus, I don't know, my pen is dying. Plus 1 yi. This is for the positive class. Likewise, yi dot x minus dot wi plus b equal to minus 1 yi. This is negative, right? So as you can clearly see in, how do I point bigger? I don't know. Maybe there's a pointer somewhere. Point bigger. I don't know. Okay, let me. Anyway, so you can see that in the top equation. Okay. In the top equation, yi is plus 1, but in the bottom equation, yi here is minus 1. So the right hand side is also plus 1. So the advantage is with this formalism, the support vector equations that define the support vector, you can generalize it to an equation like this. Where equal to 0 defines the support vectors. Okay, repeating. So I had a set of points. I'm saying two input features, two classes. I want to define a decision boundary which is at the center of two boundaries, such a way that it maximally separates the two classes. I am defining that decision rule to be x, where it's an arbitrary point, dot w plus b. W and b define the decision boundaries that, depending on the sign of that, I will call an arbitrary point one class or the other class. So then the challenge becomes, how do I obtain W and B? That becomes your training problem. As an intermediate step, as you know, that to get the center of the road, I need the two edges of the road. That's the physical meaning of these support vectors. We defined them to be like so. Positive dot W plus B as +1, -1. But to have it in a compact equation, we define effectively the label, which is +1 for positive, -1 for negative, multiplied both sides. But we know for the negative class, yi is -1. So then for any vector, need not be support vectors, I have a governing equation y dot xi dot w plus b -1 is greater than equal to 0. For the support vector, it is equal to 0, but for any other vector, this will be greater than 0. Okay? So now we effectively have a goal. Right? Suppose I have another road. This is the center. So what is my goal? Given any data, you define your support vectors. You want to maximize this distance. Right? If I maximize this distance, separating some positive classes from negative classes, you are bound to get good separation between the two data sets. Okay. So after this, it's going to become mathematics. So I think I've laid down the problem. At this stage, if there are any questions, you can ask.
So the X size that we are choosing, it will always be inside the road.
No, where? Which xi? Only
It's the-
support vector. So look at here. So I'll come to something called when you can be inside the road. Whatever we are discussing, inside the road, there can be no points. Right? So the one or two of these points through which the road passes, they are effectively the support vectors, which is governed by this equation here, equal to 0. All other points are outside the road. And your optimization problem is to make the road as wide as you can, subject to these constraints.
Is there any limit when you are choosing the boundary of the road? You said that one point, at least any 1 point, 1 plus will be there on one side, and on the other edge there will be 1 minus.
You need at least, you need at least one, right? So later
There
we
can
will
be
see.
more than one.
Sorry?
There can be more than one also.
There absolutely can be more than one. There's no constraint on how many there can be. Clearly.
In the last line, that the equation we have generalized. So if I do it like that, y dot xi dot w plus d -1 from the previous two equations, if I get, I think shouldn't it be less than equal to 0? If I subtract 1,
greater than equal to 0. Minus, so these two equations are defined only for the support vector. So if it's a support vector, it is exactly equal to 0. For everything else, you are outside that. So you're greater than 0. I mean, for everything, everything here, you're greater than 0. That's how you're defining it. Then let's not get into special cases right now. Can you allow points here and points there? That we will come to later.
Greater than 0 and less than 0. Why did you specifically choose that +1 and -1?
Purely definition, nothing more.
Okay.
Okay. So any other, because now it will get really technical. Okay, if there are no questions, then I continue. Okay, so then what is my optimization problem? I need to find an expression for D, right? I want to maximize this width of this road. So that means I need to find an expression for D. But it's quite easy. Why? Look here. So this is my positive support vector, or this is my negative, right? Yeah, sorry. Rubber. So this is my negative support vector, and that is my positive support vector, right? That defines this. So look at this line here. So x plus minus x minus, right? So if you take a, and then the center of the road, as we have said, is defined by this vector w. If you take a dot product with that direction, right? What is it? The vector or to the edges of the street, right? Defined by the two support vectors. All I need to do is take the component of that in the direction which is perpendicular to the road. This is nothing but the width. Okay. And now, so effectively you have x plus dot w minus x minus dot w. Now look at this expression. You have here x plus dot, maybe here, that's easier. Where? Yeah. See, you have x plus dot w is 1 minus b, x minus dot w is minus 1 minus b. Okay, so I can substitute them, right? So like I said, this one term, when you take the dot product, you will get 1 minus b. That term, when you take the dot product from the governing equations, you will get that. So this entire form, this width of the road will become equal to 2 upon the magnitude of the vector to the center of the road. Okay, so now you see, just from the formalism, what is your goal? You want to maximize D. So if you want to maximize D, so this you want to max, right? So that means this you have to min. And then, as happens for mathematical convenience, instead of minimizing that, you minimize this. Okay, so your entire SVM problem boils down to minimize half mod w square subject to a constraint, which is yi xi dot w plus b minus 1 equal to 0. This is your governing equation of your support vectors. Okay. So that's your problem. Does anyone know how to do a constrained extremization? What's the methodology? So it's not that I have to. Sorry?
Lagrange multipliers.
Very good. Are most of you familiar with Lagrange multipliers from classical mechanics?
Yes, sir.
Very good. Okay, so then I have nothing much to do. So then you define the governing equation. So I can have I number of such Lagrange multipliers. So I have yi x dot w plus b minus 1 equal to 0. I have to impose del L del W equal to 0 and del L del B equal to 0. Clear? Okay, so that's what the Lagrange multiplier. So you have as many Lagrange multipliers as you have support vectors. So when you take del L del B equal to 0, it's only this term that contributes. So this becomes quite easy. So for here, you get an expression that lambda I yi equal to 0. Okay? And likewise, when you take del L del, actually W is a vector, huh? Del L del W equal to 0. So for del L del W, you will receive contribution from this term, and you will also receive contribution from this term over here. So you can show that this will be equal to Wi minus lambda I yi xi vector, that is equal to 0. So W equal to lambda I yi xi. So this is your first result, and it's a remarkable result, that the vector to the middle of the road that achieves your minimization is nothing but a linear combination of your support vectors. Okay? Remember, we defined this problem. We defined this problem to maximize the road. To do that, you had to maximize 2 divided by modulus of this vector to the middle of the road W. We said, okay, for convenience, we minimize half of W square, but that is subject to the constraint equation of your support vectors. So we introduced the Lagrange multiplier framework. You take the first derivatives equal to 0. You immediately get W, which is that golden vector to the middle of the road, is nothing but a linear combination of your support vectors. Okay, so now comes the second part, that is you plug back all these expressions. So what do I do now? I have the expression for W. I want to plug that in here and there. Okay. It's tedious, but and we are also running out of time, so I'm going to go a little fast, but you check it. You will get, so it's W square, right? So you have to have 2 indices. J. So this is the W square part. Yj xj. Then I have these 2 terms, right? Yi x dot b plus b. So for that, you'll get minus lambda I yi xi dot another sum lambda j yj xj. Sorry, these are all vectors. I have to be careful. Then there will be minus lambda I yi b plus sum over lambda I. Okay. Again, repeating, we are substituting this expression for W into the Lagrange form that you have. So you have a W square part, and here you have a W over there. That's all that we are doing. Now, we had seen from this term, sum over lambda I yi equal to 0. Now try to look at this term over here. B is a constant, comes out. And we had seen sum of lambda I yi was equal to 0 from the del L del B equal to 0. So this goes to 0. And this I am not showing explicitly, except to say that you can show that this term here has the same form as the first term. You can almost see it that this term is simply a repetition of the first term. So your L becomes equal to sum over lambda i's minus half ij lambda I lambda j yi yj xi dot xj. This is a golden result in this case. So your problem is to extremize L, and once you do that, you will have your W's and the B's. But the most sorry, where did I lose everyone? Hello, can you hear me?
We just spoke about extremize L and then.
Okay. So, like we had said, in the Lagrange multiplier problem, we had gotten already an expression for the W's, which was a linear combination of the support vector. But you also have to extremize L, right, to get the final values of these W's and B's. And that's where you see this golden result over here. Of course, it is engineered because we took half W squared, that to extremize these support vectors only appear as this dot product. In some sense, this expression is quadratic in these support vectors. Okay, so that's why this becomes what's called a quadratic optimization problem. It always appears in this dot product form, and that's where we are going to see Riteshda or other. How much more time can I take? Okay, maybe I take a little more. So that's where you will see that this part is what then allows you to have non-linear boundaries, because so far we were only trying to define a linear boundary, right? One line passing through points. But how do I make that wavy if I want? Okay, so we extremize L, and the moment we extremize L, we have W's and B's, and for any arbitrary point, all you have to do is then calculate the sign of lambda I yi xi dot x plus b. Okay. So remember, what was your decision rule? Your decision rule was sine of x dot, for an arbitrary point x, once you have the W's and B's, to say if an arbitrary point is category plus or minus, we have to take the sign of x dot W plus B. But W itself is a linear combination, lambda I, Wi, lambda I, Yi, Xi. So you see that even in the decision rule, it appears as a dot product. So you don't have any X's, etc. lying around. To determine W's and B's, I have to do a quadratic optimization where I only need to know these dot products of these support vectors. But even after that, once I've obtained the W's and B's, to get the decision, am I type plus or am I type minus, it's still, I take a dot product of the arbitrary point with the support vectors. Okay, I think I'm going to stop here and then we will continue in the afternoon session. Or, sorry, how long was this session? Was it 1.5 hours or 2 hours?
I think if you have quiz to now or
No, quiz is afternoon together with everything. But I think maybe I can introduce the data sets they can use.
Yeah, so basically book time is you have another half an hour or so, but you can, if you think that you can finish it here and it is a good time to finish, you can close it now.
No, I think if I take half an hour more, that would be very good.
Yeah, so then it is okay.
Yeah. Okay, so I would like to then stop here quickly for questions, because I think we have enunciated the full problem now. If you have given points, what you do is you try to define the so-called support vectors which define your road. The center of your road is this so-called vector W. Your optimization problem is to maximize the width of the road. In order to do that, we got certain expressions subject to constraints, and therein the so-called vector to the middle of the road was just a linear combination of your support vectors. Substituting back the Lagrangian that you have to extremize only depends on the dot products of the support vector, not to any other powers. Likewise, your decision rule also depends only on this dot product. Okay?
Could you show the slide where you calculated the width?
Here.
Yeah, little below.
Sorry?
Go down a little bit.
Louder, louder.
I want to see the calculation of the
Your voice is breaking, unfortunately. If someone else understood, you want me to go up?
down, go
Sir,
down.
we want to see the expression for the width.
Okay, no, let's cover it. So your width is basically this part, right? So the edges of the road are the two support vectors, right? So I can call the width of the road, or D, is equal to x plus minus x minus dot the unit vector which is perpendicular to the road. Okay? And then we have the governing equations of the support vector, which is x plus dot W plus B equal to +1 for a positive, x minus dot W plus B equal to -1 for a negative. So x plus dot W will be 1 minus B, that will become minus 1 minus B. So this expression will become this.
So that is 2 by mod of W. How does
Yes.
it become W square in the next line?
So my goal is to maximize this width, right? So that means I can minimize W, the mod of W. I can. So
derivative.
Okay. So any further questions?
So these two support vectors are not necessary to be parallel.
So firstly, it need not be two, right? It can be more than two. But they would be parallel because suppose you have data set, you take the closest two and you define two lines coming to them. So then in that case, they would be parallel.
Okay, sir.
Yeah. But when we go to the nonlinear example, there you will see you will relax this condition.
Okay, sir.
Okay, so let us continue then very quickly. Okay, so firstly, now suppose my points are distributed like this, right? And there are more points, suppose. So what do you see? They are not linearly separable, right? So in the previous example that we had, what was the previous example? Okay, by the way, the previous example, those support vectors that we have, they are called hard margin support vectors. I'll come very quickly to why we call them hard margin support vectors. But in that example, we only had straight lines, right? You were drawing straight lines, passing through some of them, with the hope that there is no component in a no man's land. Here, there is nothing I can do to separate without issues, right? So suppose I try to draw some line here. Oh, what happened? Suppose I try to draw a line here, right? You have a violation, and this is the middle of the road in green, suppose, I don't know, there, and the other one, let's say something like that. So in the previous formalism, this is not even allowed. Why? You have so many things in no man's land. But even if you relaxed it, there's a problem that you have a plus on the other side, right? But in this problem, what is the most natural thing to do is if we can have a separation like so. If I could draw somehow a wavy line, then I could separate the classes out, right? So I would need some kind of a non-linearity to be implemented. And here we take the example or the help of what are called kernels. So I have X, nothing stops me from transforming to X to some other space, right? But it can be nonlinear. So that's really what these kernels do. So kernels are functions that map your X to some phi of X. But the advantage is I don't need to know the precise mapping. Do not need to know the precise mapping. Why? Because in the optimization problem, it appeared as x dot xj for the Lagrangian. In the decision rule, it appeared as x dot x. So you know what are called dot product spaces. All you need to know are how dot products behave with this transformation. As long as you know this, you are through in this problem. So that's why while you want a mapping that takes X to something else to be able to solve scenarios like this, but what we define it is a kernel, which is nothing but, so it takes X to the corresponding dot product. And there are various kernels, they will find them, and I'll come to that. Polynomial kernel, which is xi dot xj plus 1 to the power n, and higher the n, more the complexity. You also have what are called, this is one, you have what are called Gaussian kernels, which are where there's this distance matrix, is a Gaussian kernel. There'll be other ones called radial basis functions, etc. Those we will see when we do the exercises. Okay, so you're not limited to have straight boundaries. You can use any kernel that you want. That in principle takes you to a space where so basically you transform to a space where these potentially look linear, and you operate in that space. But the very fact that it was a quadratic, it always appeared as this. You don't need to know the exact transformation, but you need to know how the dot products behave. It is a dot product. Okay, and then finally, I will end with what is called soft margin SVM. Let me draw it carefully. Say plus, 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 plus. Suppose there's a minus, 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 minus. So if I were to draw a line separating them like that, so okay, you have violations here and there. So effectively, what we want is, can we relax the criteria that there are no points in no man's land? And how can you relax that criteria? If you define a margin of error, epsilon. So what was our governing equation? Xi dot w plus b greater than equal to 1, right? Exactly equal to 1 for a support vector, greater than 1 strictly for any arbitrary point. So this is hard margin. Now, if you make this xi dot w plus b greater than equal to 1 minus epsilon, where epsilon is strictly greater than equal to 0. So now you see, someone was asking earlier, why greater than 0, right? So the moment you are introducing this epsilon, so then you are allowing the possibility to have points within the no man's land. Clear? Just by introducing this. So you're relaxing the criteria, and then you can prove that earlier we were minimizing half mod w square. That's what we were minimizing, right? So here, the moment you introduce epsilon, you'll have the number of points that end up in the no man's land appearing with this. Your minimization problem will become like so. So larger the C, so if your C is large, you're making this term large, you're making it harder to minimize. So you're getting closer and closer to hard margin. And so hard, what we discussed. Lower the C, soft. Okay. So I hope that I have I tried to cover in reasonable amount of detail, almost explicitly, this entire support vector machine problem. It is not limited, where the highlights were that the vector to the middle of the road is a linear combination of the support vectors. The expression that extremizes the Lagrangian as well as gets the decision rule is always a dot product. It is not limited to linearly separable problems. Why? Because you can always map it to another more complex space where you only need to know dot products, hence the concept of a kernel. And finally, you don't have to be hard. I mean, points can be in no man's land, and you control that either with epsilon or with this C. Okay, so with this concept, you are fully equipped in principle if you want to code this yourself, because it's just a Lagrange multiplier. But in my case, I've given you some existing problems that you can try to solve. If there are any final questions, please ask me, because otherwise I will quickly introduce you to the data sets.
Could you show the kernels one?
I'll be sending all these notes also, okay? So don't get that if you can't take this, yes.
Here, what you have written in the first one, excited aj plus 1, this is after that?
To the power n.
To the
So
power
that
n.
determines the order of the polynomial.
And in the next one, exponential minus xi minus xj.
Just
square.
Gaussian. Divided by sigma. So you have some effectively a distance parameter in the problem.
So this is giving me the
your voice is breaking. I didn't get you. Your voice broke. I don't know if it's my internet or your internet.
I said the kernel is giving me the boundary, right? Since it is
No, kernel. No. We were discussing a problem like this, right? If my data looks like that, they are not linearly separable. I want to define a complex nonlinear boundary. So what do? In the previous problem, this wasn't possible. So what I do is I transform x to some phi x, where after this transformation, the new space that you go to, maybe they are more linearly separable. But because it was a quadratic optimization problem, I don't need to know explicitly this transformation. It's sufficient to know the dot products of any pairs of vectors. So that's what's called dot product spaces. So kernel is a trick to using the same concept to have nonlinear boundaries. By simply transforming the space, but you just need to know the expression of such dot products. Okay?
Okay.
Okay, so can you quickly... yes.
After kernel transformation, did the new space in which we go, that becomes linear?
So you will do the same exercise that you were doing with x with phi x's. So in that space, whatever is a straight line is a straight line. But when you transform back to your original space, that straight line will not look like a straight line.
Okay, it means in kernel space it is a straight line.
Yes.
Okay.
Sir?
Given some original space, can we then see which type of kernel would be useful for us? So, like, how can I tell whether
Yes.
polynomial is useful or exponential is useful?
That is where your domain knowledge comes in. I mean, uh, if you're sort of doing a clustering problem where you know that if you go far away from a point that should not have a significant impact, I would probably go with a Gaussian kernel where I know what the length scale of my problem is. Likewise, there are other radial basis functions. So if you know what your problem is, then you can take an informed decision. Otherwise, this becomes what's called hyperparameter optimization. You try different kernels, you see what gives you the best result. Again, best result is always in the form of this ROC. What is the what is the efficiency and the purity of your predictions? But then once you get the best result, that's when you try to understand why this works. I mean, there can be some greed to make n a large number, right? So that you can sort of map any complex waviness. But then you have to see whether you're overfitting or not. So the short answer is, if you know the details of your problem, you can take an informed decision. You can even design your own kernel. I mean, you don't have to take any of these forms. You find the kernel that suits you. If you don't know, then you can treat it like a hyperparameter to optimize. Okay. So just very quickly, maybe, okay, it's getting a little late, so maybe I'll skip explaining it to the next session. But all of you, please look at the message. While I had sent the data set, the explanation, the content of the data set is present in this PDF file. Maybe just download it and go through it quickly over lunch. And then we will discuss it, okay? I would like to stop here and continue in the next session. Unless there are questions, I'm happy to take more questions. Okay. So Riteshda, I'll send you the quiz in, I'll just have a tea and I'll just send you the quiz in maybe 15 to 20 minutes. Okay, so I would like to stop here. I don't know if something has to be stopped explicitly. You guys can still hear me, right?
Yes, sir.
Yes, sir.
Okay.
Yes.
I don't know if Riteshda and Partho or someone's connected. Let me just see. Hold on. All right, guys. So I think I stop here. So I'm going to disconnect. Okay. I'm going to stop here. And no, what? You're having problems downloading the data set? I gave the instructions. What's the problem? What exactly is the problem? Why can't you download the data set? Otherwise, I don't know. Anyway, if someone can't, I'll share it maybe by email, but there should be no problem in downloading the data set. You just need a Gmail account. Okay, anyway, I think I'll stop here. But if anyone downloads it, maybe share it with the whole group in the meantime. Okay, I think I'll stop here now.
Yeah. Thanks. Thanks, Rajdeep. I'll try to download the data and share with everybody to our website. So those who are having difficulty can get it. So let me try during now and next lecture. So I'll just stop the recording over here.
Yeah. And I'm just sorry, I'll just need 5 minutes extra. Can we start at 2:35?
Yeah, not a problem. Not a
Yeah,
problem.
yeah.